Alright, so in this video, one more time I'm going to run through with you the difference between standard deviation and standard error of the mean. So I'm going to give you a quick walkthrough. Some of this is a repeat of a previous video. So standard deviation, a reminder, it's a measure of how spread out your data is. It kind of tells you how far all your answers are scattered from the mean. And why that's important information is because if all you know is that your average is 10, you may be imagining, at least I would be imagining if they told me that I had taken a bunch of data and that all my numbers were very close to 10, and when I added them up and divided, I got 10. But the truth of the matter is that's not necessarily true. It's also possible that your numbers were all over the place, and when you averaged them together, you happen to get 10. And that makes a difference in an experiment, whether your numbers were really close together or whether your numbers were really spread out. So when we calculate standard deviation, if we graph that, if we add error bars and graph that, it'll give our reader an idea of how spread out our original data was. We would prefer our data be very clustered together. That's going to be better. So our steps are going to be calculate the mean. The mean is x with a line over it. Mean means the same as average. Next, for every data point, you're going to subtract the mean and square it. And then you're going to have to add all of those together. That's what this E is. It means to sum all of that up and divide it by, n is the size of your sample. So if I had 5 numbers, or in my 5 data points, n would be 5. If I had 12 data points, n would be 10. And then your last step is that you're going to take the square root of the entire thing. So I did this in class with some specific data sets. So our first data set was just 2 numbers, 7 and 13. Step 1, we get the average or the mean, and that was 10. That's 7 plus 13 and then over 2. For each number now, I'm going to subtract from the mean and add them together. So in other words, I'm going to take my first number, 7 minus 10 squared. Then my second number is 13 minus 10 squared. Like that. And I'm going to add all of those together. So that's where the sum comes in. My next step is I'm going to divide that by my population size minus 1. So in this case, the size of my population is 2, right? I have 2 numbers, so 2 minus 1, which is 1. And then in my very last step, and I put little answers to each of these. My last step, I'm going to take the square root of that. So let me pull up. So here's all the work combined. The biggest mistake I see on this, to be honest with you, is people forget to take the square root at the end. So sometimes what I like to do is do this, write out the entire thing like that, and then if you need to solve it in parts, because if you don't have a real fancy calculator, you may have to solve for this term first, then solve for this, and then plug that in and take the square root. But at least if you write the whole thing out, you'll hopefully remember all of your steps, because the biggest mistake I see, people forget to take the square root. All right, if we do this for the second set of data that was in your notes, these 5 numbers, the average is still 10, and in order to have enough time to do everything, and hopefully this didn't cut off too much at the bottom here, but here's all the work. So in this case, notice it's 5 terms long here at the top. I took each of my numbers minus 10, put it over, my sample size in this case was 5, so 5 minus 1, I get the square root of 1/4, and that gives me 0.5. So if you were doing this with 100 data points, you would use an Excel spreadsheet. There's a formula for standard deviation right in there. You just literally highlight all your data, click standard deviation, and it pops out an answer. So a real scientist is probably not going to be doing this by hand. All right, so what does this tell us? So what standard deviation tells us is, and this is something that's published, this is not, I'm not getting these numbers, I'm not making up these numbers. You're not supposed to come up with the 68 and the 95. This is calculated, mathematicians have figured this out. That when you get a standard deviation, if you graph plus or minus 1 standard deviation, it will represent where 68% of your data should lie within those error bars. So how do you graph it? So my standard deviation for set A was 4.2. So to graph that, I have my average. I go up 4.2 and down 4.2. In other words, plus or minus 4.2. And between these bars represents that 68% of the raw data, even though your reader can't see what all your data was. They don't know how many numbers you had. They don't know what the original data was. They just see your graph. So this means that 68% of that original data should be between those 2 points, which that's called an error bar. My second data set, set B, my standard deviation was 0.5, so 68% of the original data should lie between those error bars. Now, most of the time, you're not going to see one standard deviation on a graph. What you're probably going to see is 2 standard deviations. And the reason why is because 2 standard deviations represents 95% of your data. So in other words, if I graph, so how do you graph 2 standard deviations? Let me take a step back. I would take my standard deviation was 4.2, I double it. So this 8.4 is now 2 standard deviations. So now, same way I did in the other graph, I'm going to go up this time by 8.4. 2 standard deviations, I'm going to go down by 8.4. What does this mean in a graph? This means that 95% of my data, my original data, should lie within those bars. So what does that tell me? Well, that tells me my original data, even though I don't know the person's data, was very spread out. Their numbers must have been very spread out to give me that that some of their data was all the way down here, some of their data was all the way up here. And then in my second data set, I double my standard deviation. 0.5 times 2 is 1. And that would mean that 95% of my data fell within here. Now, that's all it tells us, how spread out our data is. You can't necessarily draw conclusions. I mean, I personally would say, wow, I would prefer my data not be that scattered, because obviously if my data was all close to each other, it would mean that I was more precise, that it was more consistent. But there's another piece of information, and this is where standard error of the mean comes in. How do I know if I repeat this experiment, especially this first one? With my data all over the place, if I do this experiment again, how do I know I'm going to get 10 the second time? Isn't it true, since my data is sort of all over the place, I might get a much higher or lower average? Yes, it is true. So this is where another piece of information comes in, and that's called standard error of the mean. Oh, these are some error bars. Sorry, this is just to show you that error bars can be on a bar graph or a line graph. Most of the time, I've been doing them on bar graphs, but just see how here this is a line graph. Oops, sorry about that. And you can see that there's error bars. And this other one, I think it's a bar and whiskers graph, and again, you can see error bars. So you can see error bars on all kinds of graphs. All right, so again, when you do your experiment and you get your standard deviation, it really only tells you how scattered your original data is. What if you want to know the chances that if you repeat the experiment, you would get the same thing? Standard error of the mean gives you what's called a confidence level of how sure you are that if you repeated your experiment multiple times, you'd get the same average. So let me show you. So you have a lake, it has 10,000 fish. You want to know the average size of one fish. So you catch 100 fish, and you get the average, and you calculate the standard deviation. Isn't it true you've only tested 100 fish? You haven't tested all 10,000, and it's not possible to test all 10,000. Scientists would like to have a way of predicting, if I repeat this experiment, how sure am I that I'm going to get the same average again? That if I test another 100 fish, I'd get the exact same answer. So it's based on 2 things. I think this may cut off at the bottom a little. The bigger my standard deviation, the more spread out my data is, it's going to also give me a bigger standard error of the mean. In other words, I know that my average, if I have a bigger standard deviation, it's probably less likely I'm going to get the same exact average again. Also, flip side of that, if I have a bigger sample size, I'm probably more likely to get a smaller standard error, because the more fish I test, the closer and closer I'm going to get. I mean, if I tested every single fish, I would have an exact average. So the closer I get to testing all the fish, the more confident I can be that my average is correct. So here's your formula. It predicts the accuracy of your data, the chances that your data represents a random sample. It gives you a predictability that if you repeated the experiment, what are the chances you'd get the same answer again? So just like standard deviation, if you graph with plus or minus 1 standard error of the mean, it represents a 68% confidence level. So you're 68% sure your real average should be within those bars. 2 standard errors of the mean, 95% confidence that your data should be within those bars. Now, I'm not going to calculate it for both. I actually do have the answers here for both. But the way you would calculate it is you would take your standard deviation. So in our original data, this was our original data set, our standard deviation was 4.2 over, my sample size was just 2 numbers, so it would be 4.2 over the square root of 2. That's how I got 3. For this one, my standard deviation was 0.5. I had 5 numbers in my sample, and when you divide that out, you get 0.3. So that's how you calculate it. So it comes from your standard deviation, but it gives you more information. So here's the bottom line. If you graph plus or minus 2 standard errors of the mean, and your error bars do not overlap, you would conclude that there is a statistical difference between those 2 groups. If the error bars overlap, you conclude there's no statistical difference between those 2 groups. And this is because the true average, remember, can lie anywhere within those bars. Now, let me show you what I mean in a picture, and maybe this will help. So here is my data for ethanol. And pretend like, because remember, they have to tell you what the error bars mean. So let's pretend like the error bars represent 2 standard errors of the mean. Another way they might write this is they may say that the error bars represent 95% confidence. Confidence refers to standard error of the mean, and the 95 tells me it's 2. Anyway, so think of it this way. Even though this is the average I got for ethanol, my standard error bars are telling me that I'm 95% confident that my real average, if I repeated this, might fall anywhere in this range. So think of your bar graph, instead of thinking of this as a distinct line, think of it as like a fuzzy area, that my bar could really, in real life, if I repeated this multiple times, my bar graph would end anywhere in here. So if I redraw all of these as fuzzy areas, that my real graph might be anywhere in here. It's sort of like my uncertainty. So the question is there a statistical difference between these different groups? Well, let's look at each one. Ethanol and saccharin. So here's what I mean about the bars overlapping. If I look at the bottom of my ethanol, which my real average could be as low as this, and the top of my saccharin, see my overlap. These 2 bars intersect each other. They overlap. So I would conclude no statistical difference. Because in reality, unless I can get those error bars smaller by repeating my experiment, it's possible that there really isn't a difference between these. This one might be as low as my lowest bar. This could be as high as my highest bar. So in reality, this is a gray area. I can't say there's a difference. Saccharin and salt, still no difference. Now these just touch, but isn't that still true that this could be as low as this and this could be as high as this, in which case they would be the same? So I'm still going to say no statistical difference. Ethanol and salt, yes. Ethanol, I've made a big mess here, but ethanol, this is the lowest, this is my highest. See the gap here? So yes, so no on this and this, yes on this. Salt and sucrose, also yes, there's a gap. Here to here, definitely a gap. And then salt and water, no, they overlap. So that's the bottom line on standard error of the mean. I hope this clarifies it for you. So standard deviation tells us how clustered our data is. Smaller is better. I mean, it means our data was more precise. But what you really want to put on a graph to compare the bars is standard error of the mean, because it tells us a range of where the true value should lie. So 2 standard errors of the mean means that we're 95% confident that our true average should lie within those error bars. And if error bars overlap between 2 groups, they're basically telling you there's not a statistical difference. We can't conclude that. There's not enough evidence. I mean, I wouldn't say that there can't possibly be, but until you can do more evidence and get those error bars smaller, we can't say for sure. So you cannot conclude that there's a statistical difference. Only if there's a gap. And even if there's a gap, they actually still say that it's still possible. We have to test further, but you'd likely have a statistical difference.